Hello, my name is Kareem Khalifa, and today I'll be introducing you to proofs. Here's how we'll proceed today. First, I'll explain why this matters. Then, I'll draw a useful analogy between proofs and games. Then we'll look at proofs with identity, where we're trying to show that an argument is valid. And finally, we'll engage in proofs of invalidity, or proofs of non-consequence. So first of all, why do proofs matter? Recall from the last lesson that we saw that the goal of logic was to distinguish valid from invalid arguments. But we don't yet have a method for showing that an argument's valid or showing that it's invalid. That's what we're going to get the rudiments of today. Second, remember on the first day of class, I told you that logic is basically a weight room for your mind, right? Proofs, I think, exemplify this, where you're really in an environment designed to really sharpen your skills at ferreting out valid arguments and distinguishing them from invalid arguments. Speaking of valid arguments, here's just a quick reminder. An argument is valid if and only if there is no possible way for all of its premises to be true when its conclusion is false. I repeat, this is the single most important concept in the class. This is the single most important concept in the class. You with me? I'd like to suggest a useful analogy. Proofs are like games. In many games, including football or soccer, if you're an American like myself, you have an initial field position, and then you move down the field in accordance with various rules of play, such as not violating offsides or not tripping your opponent, no handballs, etc. And eventually, you want to try and score a goal. And I want to suggest there's an analogous structure with a proof. The analog to initial field position in a proof are your premises. These are the assumptions that you can take for granted in the proof. And just like football players can't move down the field in any arbitrary fashion that they want, they have to obey the various rules of soccer or football, you have to do the same thing in logic. You have to obey the basic rules of inference, and we'll get into what those are in a minute. Finally, just as a goal is a desirable end state in soccer or football, the conclusion is a desirable end state in a proof. So from our previous lectures, you should know what premises and conclusions are already. However, basic rules of inference are something new. There's a bunch of these, and we're just going to introduce you to two of them. There's more that are going to be coming in the upcoming lectures. Eventually, we'll be proving things with all sorts of operators, if then, all, some, or, not, etc. But today we're just going to focus on identity because it's very familiar to you and it will help to exemplify the basic mechanics of a proof, and you'll see that we can add more flesh to the bones of what we're looking at today. There's two basic rules to using the identity operator in a proof. The first is what we call identity elimination, and typically in a proof we'll just put that as equals elim. Right? What this says is if B equals C, then whatever holds of B holds of C. In other words, you can always replace B with C in a proof. Let's look at a very simple proof involving identity elimination and an example from last class. The first premise says Professor Khalifa and Kareem name the same object, name the same individual. The second premise says that Professor Khalifa teaches at Middlebury College. And from these two premises, it's pretty clear that we can infer that Kareem teaches at Middlebury College. Notice that the conclusion, statement 3, follows from identity elimination plus the premises 1 and 2. So we mark it as indicated in the bright yellow. We put equals elim 1, 2. Let's walk through this more carefully. We see the general rule here, and what we see is there's an interesting mapping, right? So what's playing the role of B in this is Prof. Khalifa, and what's playing the role of C is Kareem. Next, in order to keep the mapping going, we need to see what holds of B, that is, what holds of Professor Khalifa. As you can see, I teach at Middlebury College. Finally, identity elimination says that whatever holds of B holds of C. So in this case, whatever holds of Professor Khalifa, namely that I teach at Middlebury College, is also going to hold of Kareem, and that's exactly what we see in the conclusion. So we see that the mapping is perfect, and that's what allows us to apply this rule in this particular proof. Final point I want to make about this example is the mapping has to be really, really tight. If we're thinking of logic on analogy with a game, we've got very strict referees. Let's look at premise 1 in our proof. Prof. Khalifa equals Kareem. If you notice, the color coordination there goes yellow, purple, green, and if you look at the rule, the color coordination goes yellow, purple, green. It's because of this tight mapping between B equals C in the rule and Prof. Khalifa equals Kareem in premise 1 that we know to cite premise 1 on line 3 of our proof. Similarly, the tight mapping between whatever holds of B in our formulation of identity elimination and premise 2 tells us that we ought to cite premise 2 as a justification for line 3 of our proof. There's a second basic rule associated with identity in proofs. It's called identity introduction. We abbreviate it as equals intro in the proof, and it just says sentences of the form B equals B are always true in first-order logic. In a proof, this means you can pop them in wherever you need them. Suppose we're given the premise that Prof. Khalifa is identical to Kareem, and we want to prove that Kareem is then identical to Prof. Khalifa. This may seem obvious, but remember I told you that in logic we have cranky referees. Right? So if you look, we have no rule that just allows us to reverse the equal sign, even though we know that it's a symmetric relation. Right, so how do we do this? We use a 1-2 punch. We use identity introduction followed by identity elimination. Let me talk you through this 1-2 punch. First, we use identity introduction and show that Prof. Khalifa is identical to Prof. Khalifa. Note that you don't need to put any numbers here because this is always true. Next, you're moving down the field, right? You move further with line 2, and now you can use both 1 and 2 to get yourself to your desired conclusion. You use them in conjunction with identity elimination, and that gives us what we were trying to prove, that Kareem is identical to Prof. Khalifa. Let's talk through this a little bit more. Remember, tight mappings are crucial for being able to apply the rules. Now, if you look, all of these mappings are identical to the previous proof we looked at, which just involved identity elimination. The difference is simply in what holds of B, and by implication, what holds of C. Let's look at that a bit more carefully. If we're going to get this mapping going, we need to be clear about what holds of B, that is, what holds of Professor Khalifa. And that's precisely what's in line 2. What does that say? Line 2 says that what holds of Professor Khalifa is that he's identical to Professor Khalifa. So by identity elimination, that means that Kareem is also identical to Professor Khalifa. And we get our proof. So recall, the goal of logic is not just to identify valid arguments, but also to identify invalid arguments. What the textbook calls proofs of non-consequence, which I think is barbarous, so we're going to stick with proofs of invalidity because it sounds better to my ear. Speaking of valid arguments, here's just a quick reminder. An argument is valid if and only if there is no possible way for all of its premises to be true when its conclusion is false. I repeat, this is the single most important concept in the class. This is the single most important concept in the class. You with me? Consequently, an argument is invalid if and only if there is some possible way for all of its premises to be true when its conclusion is false. A counterexample is simply some possible way for all of an argument's premises to be true when its conclusion is false. So when we construct a counterexample, we prove that an argument is invalid. In this class, we'll construct counterexamples using Tarski's world. Let's take an example. Here's the argument. The premises are B is to the left of C, B is to the right of D, D is in the same row as E, and the conclusion is that E is to the right of C. I'm going to tell you in advance that this is invalid, but now what I want to do is show you how to construct a counterexample. So what we're trying to do is create a counterexample in which all of the premises are true and the conclusion is false. Let's start with the first two premises because they're pretty straightforward. Here we see that B is in fact to the left of C, and B is to the right of D. So we have to be careful with this third premise, because depending on where we put E, we might trick ourselves into thinking that the argument is valid when in fact it's invalid. Let me give you an example where we trick ourselves. All right, here's a good way to trick myself. Suppose I put E on the far right. Well, then all of the premises are going to be true, right? You can see that E is in the same row as D, and then we already showed that the other two premises are true. And furthermore, the conclusion is true. But this doesn't show us that the argument's valid. All that this shows us is that there is some way that the premises can all be true when the conclusion is true. But that's not the definition of validity, remember? The definition of validity is that there's no way for all of the premises to be true when the conclusion is false. So we haven't shown anything yet. What you want to do is make a concerted effort to make all of the premises true and the conclusion false. You want to really work hard to generate a counterexample. You're trying to be a critic here of this argument, maybe is a good way to think about it. So in this particular context, that means that I'm going to try to find some way in which E can be on the same row as D so that third premise is true. And at the same time, I want to try and see if I can put E to the left of C so that I falsify the conclusion of this argument. That will generate a counterexample. Here's one way to do that. I should say that there's a bunch of other ways to do it too. The nice thing about Tarski's world is that you can check these things, and I'll show you very briefly how to do that. So here's our model now set up in Tarski's world. You can see that I've just set up the blocks exactly in the same sequence that I did on the previous slide. All I have to do is click that button in the upper right-hand corner, and it will basically assign values to all the premises in the conclusion. And what I'm looking for is to see if I can get all the premises to be true and the conclusion false. This is exactly the idea behind an invalid argument and a counterexample. So here's when I know I have a good counterexample. It's basically Tarski's world tells me that all the premises are true and the conclusion is false based on what I did on the left-hand side there with the blocks and the checkerboard. So here's a really quick recap. Much like a game, we can prove an argument is valid by advancing from our premises to our conclusion, obviously in accordance with the rules of inference, of which we have two: identity introduction and identity elimination. Second, we prove an argument is invalid by constructing a single counterexample in which all of the premises are true and the conclusion is false. Thanks, and I'll see you at the next lesson.